Hey everyone, welcome back to Learn Math by Example at Sam's Hub. We've already explored the fundamental truths of accuracy and tackled some mixed review problems. Today, in Lesson 3 of our first unit in Math AI, we're taking a crucial step further. We're going to unlock the deeper truths of accuracy by diving into three absolutely vital concepts: lower and upper bounds, measurement error, and percentage error. These ideas are absolutely essential for your Math AI course, whether they pop up as standalone questions or as a small but critical part of a much bigger problem. Well, sometimes they ask about it in Math AA course as well. My goal for you today is to leave feeling super comfortable with all of them. So grab your notebook, your GDC, and let's get started. Alright. Now, starting with lower and upper bounds of accuracy. Now, what are they, really? Well, whenever we measure something or even rounded number, there's always a tiny bit of uncertainty. Now, the lower bound is the smallest possible value the original measurement could have been, and still round to our given number. And the upper bound is the largest possible value the original measurement could have been. Now, think of it like this. If you measure a length as exactly 5 centimeters, but your ruler is only accurate to the nearest whole centimeter, that 5 actually represents a range. The true length could be a little less or a little more than 5. Now, the trick to finding these bounds is always considering half of the degree of accuracy. If a number is rounded to the nearest whole number, its degree of accuracy is 1. So half of that is 0.5. So you subtract 0.5 for the lower bound, and you add 0.5 for the upper bound. Let's look at some examples to make this crystal clear. Now, in example 1, a length is measured as 12.3 centimeters, rounded to one decimal place. Find its lower and upper bounds. Here, the number is 12.3, and it's rounded to one decimal place. That means our degree of accuracy is 0.1. So half of our degree of accuracy is 0.1 divided by 2, which is 0.05. Now, for the lower bound, we subtract 0.05 from 12.3. This gives us 12.25 centimeters. Now, for the upper bound, we add 0.05 to 12.3, and this gives us 12.35 centimeters. So the actual length L is between 12.25 inclusive and 12.35 exclusive. Now notice that the equality sign for the upper bound is less than strictly 12.35 because 12.35 would round up to 12.4, which is not 12.3. Now in example 2, the mass of a bag of rice is 500 grams, rounded to the nearest 10 grams. Find its lower and upper bounds. Now in this case, the measurement is 500 grams, and it's rounded to the nearest 10 grams. So our degree of accuracy is 10. Now half of that is 10 over 2, which is 5. Now the lower bound is 500 minus 5, which is 495 grams, and the upper bound becomes 500 plus 5, which is 505 grams. So the mass is between 495 grams inclusive and 505 grams exclusive. Next up, let's talk about measurement error. Now, this is a super straightforward concept, but critical for understanding how accurate our data truly is. Measurement error is simply the difference between the actual or true value and the estimated or measured value. We often denote the actual value as V of A and the estimated value as V of E. So the formula is simply V of A minus V of E. The result can be positive or negative, indicating if our measurement was an overestimate or an underestimate. Let's quickly see this in action. Now in example 1, a student measures the length of a table to be 150 centimeters. The actual length of the table is 152 centimeters. Calculate the measurement error. Here, V of A is 152 centimeters and V of E is 150 centimeters. So the measurement error is 152 minus 150, which is 2 centimeters. This means the measurement was 2 centimeters under the actual value, so this is an underestimate. In example 2, a balance reads 25.5 grams for a substance with known mass of 25 grams. Calculate the measurement error. Now in this case, V of A is 25 grams and V of E is 25.5 grams. So the error is 25 minus 25.5, which is minus 0.5 grams. This negative sign tells us the measurement was an overestimate. While simple measurement error is useful, sometimes we need to understand how significant that error is relative to the actual value. That's where percentage error comes in. It expresses the error as percentage of the actual value. Now, the formula is very easy and very straightforward. It is the absolute value of the difference between the actual and estimated values divided by the actual value and then multiplied by 100%. Now, we use the absolute value because we are interested in the magnitude of the error and not whether it's an overestimate or an underestimate. We want the percentage to be always positive. Let's apply this formula. Using the same table example from before, the actual length was 152 centimeters and the measured length was 150 centimeters. Now here we have to calculate now the percentage of error. We know that the actual value was 152 and the estimated value is 150. So this means that the absolute value of the difference becomes 2. And now we're going to have 2 over the actual value, which is 152, times 100%. Now this gives us approximately 1.32% to 2 decimal places. And relatively small percentage of error indicates good accuracy. Now if you look at example 2, a student estimates a jar contains 200 beads and the actual number of beads was 210. Now calculate the percentage of error. In this case, if we apply the formula, V of A is 210 and V of E is 200. So the difference is 10 in absolute value. And now divided by 210 and then multiplied by 100% to get approximately 4.76%. Performing these calculations, especially with decimal numbers, can be prone to small errors if you're doing them manually. Now this is where your graphical display calculator or GDC becomes an incredibly powerful tool. Alright, it's time to put all of our knowledge from today's lesson and even previous lessons to the ultimate test. Here's an external exam question that combines the concepts we've discussed. Now take a moment to pause the video now, read the question carefully, and try to solve it on your own. Pay attention to keywords, what's being asked, and which formulas you'll need. Welcome back. Let's walk through the solution step by step. In part 1, we have to find the lower and the upper bounds. Now, the measured length is 250 centimeters to the nearest centimeter. So the degree of accuracy is 1 centimeters. Half of that is 0.5 centimeters. So now this means that the lower bound is 250 minus 0.5, which is 249.5 centimeters. And the upper bound is 250 plus 0.5, which is 250.5 centimeters. So L becomes between 249.5 centimeters inclusive and 250.5 centimeters exclusive. For part B, we have to calculate the measurement error. Now, we know that the true length is 249.7 centimeters. And the measured length is 250 centimeters to the nearest centimeter. So V of A is 249.7 centimeters and V estimated is 250 centimeters. The measurement of error is V of A minus V of E, which means it's 249.7 minus 250, which is minus 0.3 centimeters. This is an overestimate. In the third part, we have to calculate the percentage error and round the answer to 2 decimal places. Now, we have the percentage of error formula is V of A minus V of E in absolute value divided by V of A times 100%. So this means that the percentage of error is 249.7 minus 250 over 249.7 times 100, which will give us 0.3 over 249.7 times 100, which is about 0.12% to 2 decimal places. Now, by breaking down the question and applying our formulas precisely, we can confidently solve even complex exam problems. Now, it's your turn for a quick check. I've got a couple of quiz questions for you. Again, pause the video, work them out, and then hit play to check your answers. Fantastic work today. Now you've just unlocked a deeper understanding of accuracy. Remember, we covered lower and upper bounds, how to find the minimum and maximum possible values of a rounded measurement, the measurement of error, which is the direct difference between the actual and the estimated values, and the percentage of error, the relative error expressed as a percentage, which is always positive. Now these concepts are fundamental in Math AI and will ensure your calculations and interpretations are precise and reliable. To truly solidify your understanding, practice is key. I've put together a dedicated blog post with even more practice problems for this lesson. You can find the link in the description below. And make sure you subscribe to the channel and check out the full first unit Math AI playlist to keep up with all the lessons. Our next video will build up on these concepts, so you don't want to miss it. Thanks for watching, and I'll see you in the next lesson.